All right, we'll get started. So, welcome to the first ever For Students by Students lecture. My name is Mohamed Nassif. I'm a third-year PhD student at Georgia Tech with the SSDL and working with Dr. Gunter. I'm a current board member of SAESAC and the speaker for today. So for those of you who don't know, For Students by Students is a new initiative of SAESAC for the student community to engage in gaining new knowledge and to familiarize with frequently used tools. The FSBS lecture series will focus on sharing minor technical skills or knowledge across to students from undergraduate to graduate level that can be utilized in coursework and/or research. Each lecture in this series will be developed and delivered by a graduate student with considerable experience in that area, tailored to AE applications. These lectures will have a new topic every month based on suggestions by students, mainly in the graduate community. So as I said, I'm a third-year PhD student with Dr. Gunter. I work on developing simulations for using small sats for planetary exploration, mainly icy moon missions. So a lot of my work involves integrating in numerical techniques, for which ODE45 has been quite useful. So here's a list of things that we'll go through today. We'll start off with some introduction to basic differential equations. I'll give some examples of first order and second order and non-analytically solvable equations. Then we'll move on to what is numerical integration, just briefly. Then we'll go to an introduction to ODE45, give an example of that, how to use it with a first order differential equation. And we'll talk about what state space forms are and why they're required. And we'll give an ODE45 example with the state space form for second order differential equation. Then we'll look at some more examples of ODE45, how that apply to AE applications. Note that you're welcome to take notes, code alongside while I give the presentation, but I won't be doing any active coding. I will be showing code snippets and results so that it's easier and I can avoid potential MATLAB software issues that might cause delays. You're free to ask me questions, but please do not ask me, hey, why is my code not working? This is not a coding class. We only got 50 minutes to go through all the topics. I want to make sure you guys have actually got the basics of using this tool. So let's look at some terminology. First up, we have, if you have taken a calculus class in high school or in your college in like first year, second year, you'll be familiar with these terms. A linear equation is just something that just has first powers of the main variable. So in this case, x is our main variable, and this is a linear equation. This is a linear equation in a second derivative. In most, if not all, you can easily find solutions to these kind of differential equations. A non-linear equation, on the other hand, is the opposite of a linear equation. It does not have a first power of x. As you can see, this is x to the minus 1. Or it also has trig functions with the main variable, which is x here. Some equations have solutions to them, but a lot of complex nonlinear equations, they don't have any analytical solutions. ODEs are just differential equations that have only one independent variable. What does independent variable mean? Is that you have a function of x, you have a function x as a function of t, and you're taking derivative with respect to that variable t. You have a vector equation, R, which is a position, is x, y, and z. All three are dependent on time, but you're taking the derivative with respect to time. So that's an ordinary differential equation. Partial differential equation, they have multiple independent variables. So if you have a function that is dependent on x1, x2, x3, and you're taking derivative with respect to x1, and that's represented by a partial derivative symbol. Same thing with those x2 and x3. In the case of R, it would be with respect to x, y, or z, because that's what the position variables are. Order of a differential equation. It's the highest derivative in the differential equation. So here, this order is a second order differential equation. This is also a second order. If we only had these two terms, it would be a first order differential equation. So let's look at a first order differential equation. You have x dot equals dx dt equals t. Pretty simple, can be solved analytically, and it's given by the solution. X of t is t squared over 2 plus c. Now, we apply initial conditions, x at time 0 is equal to 0. You get this nice looking expression, and then you plot it. It's a simple parabolic, and I've only plotted from 0 to 5. So pretty straightforward, nothing too hard there. Let's look at a more complex example. Now, if I tell you, can you tell me what this solution looks like? It's going to be a bit hard. But using some techniques like separation of variables and integration by parts, and using the initial conditions of x of 0 equals to -1, or whatever initial conditions you want, you can get a solution. I have used x of 0 equal -1, and this is the solution I got, which is complicated looking. It's not as straightforward as we saw in the previous slide. What about this? Some of you may have seen this. This is a simple pendulum, frictionless simple pendulum. The equation of motion is given by this form here. And as you can see, this is a nonlinear equation because you have a derivative of theta dependent on the sign of theta. So there's no analytical expression possible because there's a sign term. But how do you solve these kind of equations? Well, you can make it linear. If you say that you're only looking at small angles of theta, well, you can approximate sine theta approximate with theta, and then you have theta double dot equals something times theta, and that's pretty straightforward. Or you can solve it using numerical integration. A lot of the times, a lot of dynamical systems that we might encounter in aerospace or even any other field are nonlinear by default. So you'll have to account for these. You can always linearize them, but sometimes it may not be possible. So you'd want to use numerical integration. Some examples of more dynamical system. Here's a mass spring damper. This is without damping, and this is with damping. Myself being a spacecraft student, I'm going to give an example of a spacecraft system. So this is a two-body orbit problem for a spacecraft orbiting a planetary body, or a smaller planetary body orbiting a larger planetary body. So it's given by this expression. The acceleration dependent on position. So what is numerical integration? Simple. It's a method of approximating the integral. You might have seen some of these before. Simple example are the Riemann sums. You approximate an integral by finite rectangles. You can take a lower sum or you can take an upper sum. And as you keep changing the width of these rectangles, you can get a more accurate result. That's great, but it requires you to know the value of the function at every single point for whatever fine grid you might have. It also requires you to know what the starting value and the end value is. And a lot of times, you only know what the starting value is. You don't know what the ending value. For example, with the spacecraft system, you know where the spacecraft is at initial time because that's where you put it with a rocket launch. But you don't know where it will be 10 days from now. You want to know what that is. So you would want it, this may not work all the time. So you want to use some more information. Here you just have values of the points, but you also might want to use the derivative of the differential equation. So the derivative is the slope of a function, and this can tell you whether it's slope like this, or are you at this point, or are you going down or going up. That helps you better understand what the curve looks like. So from an Argentine differential equation and an initial value problem, we have the initial time at which we start. We know what the initial x is, the function value at that point, and we know what the slope is because that's given by the differential equation. But we don't know x of t. Note that I'm only considering a first order equations. We'll talk about the second order and higher order stuff later. But we don't know what x of t is at all times t. That's what we want to find out. So what techniques like ODE45 do is that they find the nearby values of x of t. So they start here, they use the slope to draw a slope from here, and then they approximate the next point. And they keep doing that until they can find a curve that best fits the actual value. Some of these techniques are called Euler's method. They're the simplest, but they're less accurate. So something called the midpoint method. And something that's more common is called the Runge-Kutta method. It's more accurate than Euler because it uses repeated function evaluations at different points. And you can solve any order equation. It's basically you can solve any order, and most common is fourth order expansion. So I'm not going to go too much into what fourth order Runge-Kutta means or sixth order. It just means that the higher the order, the more function evaluations you have a better chance of being accurate. ODE45 is one such function in MATLAB that utilizes a Runge-Kutta fourth order expansion. Of course, now with a lot of function evaluations, it takes a lot of time. So you want to have a nice balance between what's good enough versus how much time you actually want to spend getting the solution. So here's just a screenshot from MATLAB's page, find right here. It's a list of all their ODE solvers that they have. So ODE45, as you can see, it's a medium accuracy. So because it's fourth order, you can get higher order Runge-Kutta methods, but at the cost of computational time. So it's about medium accuracy, and you can see it says most of the time ODE45 shall be the first solver you try. You have other methods, ODE23, ODE113, and then some other examples that you're free to go look, but I'll only focus on ODE45. So, like I said, ODE45 is a built-in MATLAB function that utilizes the Runge-Kutta 4-5 method. The command is this. This is the MATLAB command that you will use. But there are things that come before it, there are things that will be used by it. So let's look at it. T is just an array of time intervals, or whatever the denominator or independent variable is. Here I'm considering everything with respect to T because time is just simple for dynamical systems. X is the function that you want to get. It's the array of x of t at each of those time steps. This is the MATLAB solver, so it'll be ODE45. If you use something else, it'll be ODE23 or 113, whatever you use. At func, it's a function that contains the derivatives. So this is a function where you define the differential equation, and we'll see what that is in a bit. T-span is it's basically the same t right here that contains the time intervals. Usually, it's just your initial time and your final time, but you can also specify a grid, evenly spaced grid between initial time and final time. In it is, like we said, the initial value problem. So this is where you define a vector containing specifying the initial conditions. So here we have just x. Now, if we have an x, y, z, we're looking at a position, we'll have 3 initial conditions. So we'll see that later. Right now, we're only looking at one initial condition because just one variable x. Options, these are the error settings for the solver. So it's basically how well you want the solver. So smaller the error tolerance, the longer it takes to solve. The less the error tolerance, you might not get an accurate result, but it'll solve fast. And constants are just anything that appear in the differential equation that's not dependent on x or t that you might want to specify. For example, in the mass spring damper equation, you have a mass, you have k, and you have c. You can just specify them here. Of course, there'll be m, k, c. So how do you use ODE45? The 4-step procedure, usually 3. The first step is define your inputs and solver settings in a script. Write the differential equation as a function in a separate script. Then use the solver in the script from step 1 and run. Plot results. So if this is optional, you might not always want to plot, but it's good to always visualize what you're getting to make sure it's what you think you should be getting. So let's look at these steps in detail. By solving this equation, the first one that we saw, x dot equals dx over dt equals t. First, we define our inputs and solver settings in a script. So this is a script. I said my first ODE.m. So these are the steps. These are the steps that you do. You would set your ODE45 error tolerance. So I said error tolerance is 10 to the minus 13. The lowest is 1e minus 16. So that's the machine precision, machine epsilon. But you can ignore if you don't want this precision. You can just use default, which is something like 1e minus 9 or something like that. If you don't even care about what settings you want, you can just set options equal to just blank with these array square braces. And if you don't want that, if you actually want to define a tolerance, you would set options is equal to ODE set relative tolerance, absolute tolerance, and then tolerance value. So you want to define your time duration. T-span, that I said, is from 0 to 5. So I'm only doing for 5 seconds. You can do 0 is to 5 to get an evenly spaced grid, or you can do 0. This will break it up into 1, 2, 3, 4, 5. This will make it even more finer, 0.01 for each interval. And then we set the initial conditions. I'm just saying init is equal to 0 because we set x of 0 equal to 0 in our example. Now, write the differential equation as a function in a separate script. So x dot equals dx over dt equals t. Now, how do we write that? Well, we make a new script called func.m, or whatever you want to name. We have the syntax function dx equals func, and then t comma x, because those are our two variables. This is the independent variable, and this is the variable that we want to solve for. And we basically say dx equal t, which is what this expression is. So this is just represented by dx, which is the output for the function, and t is just what the differential equation is, and you just end, and that's pretty much it. Use the solver in a script from step 1 and run. So we look at the same script again, but except we have this new line of code here. We call the solver. There are no constants here, so we don't have to worry about that. So we say tx equals ODE45 at func, tspan, and it options, and we've defined all 4 of them before. And you want to make sure func is in the same file, or you have added to your path and all that kind of stuff. Now plotting, let's look at it. In blue is the results from ODE45. In red, it's the true solution. And as you can see, it agrees pretty well. Now, what happens if we custom set t-span? As I mentioned, I just set t-span as 0 to 5 and let ODE figure out what intervals to use. Let's look at a case where we fix the size of t-span to be evenly spaced grids with just 1 second each. So, clearly, it does a good job of showing what the function looks like, but it's not the accurate solution because you don't have a fine grid. You want to make it more fine because sometimes ODE will make it fine for you, or sometimes ODE might not be able to do it. So you have to manually give it a finer grid. So what do you do when you have constants? And I suppose the differential equation we looked at, dx over dt, instead of just t, it has at. Now, the only thing you'll change is in my first ODE.m, you will call the solver ex, and then after options, you'll put in a, and you'll just define a is equal to 5 or 6, whatever you want to define. And then you'll modify func.m to have an additional input, a, which corresponds to here, and dx equal at. Note that you want to make sure if you have, at plus b, then a and b are here, and then the same order goes in here because it's going to take what you put in. You want to make sure you're consistent with the ordering of your constants. Now let's look at a second example of a simple pendulum. The equation, as you can see, is a second order differential equation. But how do we write this in MATLAB? Because if you notice, here it's just a first order. How do you put dx, second derivative here? You can't just say d2x because MATLAB doesn't know that. What you can do is we want to represent. So in this case, my main variable is theta, and independent is still time. So we need something called first order equations to solve ODE45. We cannot solve ODE45 with a second order differential equation. We need to convert it to first order. How do we do that? So we'll just take a pause from ODE45 and we'll learn about state space form. If you have taken controls or system dynamics, you might be familiar with what state space form is. But we'll just learn about it in brief. The state space form, it's a form of converting differential equations to form of vectors and matrices. It's useful because we can make all of our higher order differential equations into first order equations. The number of first order equations will be equal to the highest order differential equation. So if you have a second order differential equations, you will have 2 first order equations. If you have a fourth order equation, then you'll have 8 first order differential equations. So let's look at the simple pendulum example. So let's define a state variable x. So state vector x, and we have two elements that are called state variables, x1 and x2. This is simple. It's a vector in MATLAB or an array in MATLAB, and you can easily implement this. Let's say x1 is theta and x2 is theta dot. Now let's just differentiate this with respect to time. What basically differentiating each element, so x dot 1, x dot 2, which is theta and theta dot, become theta dot here and then theta double dot here. But we know what theta dot is. Theta dot is just right here. This is x2. This element is just x2. And what is theta double dot? It's the equation we had right here, right? We get x2, and then we know what theta is. Theta is just x1. So we put this as x1. So now that's state space form. You have this equation. It's all simple. You just basically put all your variables. So your state vector will contain the order of differential equations. If it's second order, you'll have two state variables. If it's a third order, you'll have three state variables. And you will go up to n-1 order. So if the highest order is second, then you only go up to the first order derivative here. And then when you take derivatives, you'll get the second order derivative right here. You plug in this equation. Now we have this. This is all good. How do we write this in MATLAB? Well, we just simple. We have in state space form this equation right here. It's all first order. You have something times the first order, something multiplying second order. First order again. In MATLAB, we have this. So we just made one change here because we have now two constants, G and L. So we say G and L. But here, X, as we said, is no longer a scalar. It's a state vector. So it has two. So you want to define dx. So your output will also have. So this is dx. So dx is 0 is 2 by 1. So you always want to define a vector. So if it's 5 by 1, 6 by n, whatever you want to define. And you set dx of 1, which is this. First element is equal to x of 2, as we've said right here. And then the second element, dx of 2, is equal to minus gl p over l times sine x of 1. It's pretty simple. In this function, x of 1 is your angle, x of 2 is your angular velocity, which is theta dot, and that's what it looks at right here. And your output here is your velocity and acceleration. And it changes to the main script. Basically, you define your constants again right here. I changed some settings here, so I changed my t-span to be 0 to 10 seconds. And then I changed my initial conditions to say that let's start from 90 degrees. So basically, let's start from a flat line and with 0 velocity. And then we call the solver here. So note that init is now no longer just one variable that I said 0. It's two variables because this is your initial position, initial velocity. So init should match what your state vector is. Now, you put G and L in the same order that it's used in your function right here, G and L. So now, plotting. The output X will now have two columns. Before, we just had one column for each time step. We had the value of X. But now, we have X's two variables. X has position, X has as an angular position and angular velocity. So each column will represent a state variable. First column is for your angle theta. Second column is angular velocity. So let's take a look at the results. This is simple pendulum. So when you understand, you take a look at it, is that you start, blue is your position. So you're starting at pi over 2, which is like 1.7. I've just plotted them same scale, so that's why they're just a bit distorted. But you start at 90 degrees and your initial angular velocity is 0, which makes sense. As you get to theta equal to 0, your position or your velocity is maximum. And then as you go to the other end of your position, or your angular position, the velocity is 0, which makes sense. Then it keeps going, basically oscillating as you would expect. note that this is still a frictionless system. So, there's no air resistance anything. If you drop a pendulum, it's going to keep swinging forever. Now, here's your simple animation. It's slightly more than just using a plot command, but nothing too hard. You see, it starts from there, and I think I ended the video too early. But that's basically the animation. Look at that again. And there we go. I'm going to take a couple minutes pause and see if there are any questions that people want to ask. You can post your questions on the chat, or I'm not sure if there's a way to unmute people. I unmuted everyone. So if you have any questions, feel free to chat it in. I'm going to pause for like a couple of minutes just to make sure you guys have got. Okay, we'll have some time for questions again at the end. If we want to interact live. What function did I use to animate the output? Basically, I'll just go here. Basically, I set what I plotted two conditions essentially, and I fixed this to be, it's 0, 0, and then I just set this. The coordinates of this will be sine and cosine because that's how you find what the angle is. So in x and y terms, it's just sine and cosine, and then you just plot it at every time step or every 10 seconds. Or every 5 seconds, or however you want to plot it, and then you use something called draw now. It's just a MATLAB command that you basically loop. You run it in a for loop, so you're basically just plotting a single point in every 5 seconds. You're plotting a point, and then you're deleting that point, and then you keep repeating that again and again until you're satisfied with the animation. All right, so let's continue. Let's look at the state space form for another example. Equation for a mass spring damper system. Note that you can use this for any differential equation that you like, whatever they may be. I'm giving simple pendulum, mass spring damper because these are some of the things that you will encounter as aerospace students, in your vibrations class or system dynamics. So I just wanted to make it simple, but I don't want to have like complex, just put in aircraft equations of motion because those are complicated, and unless you have taken aircraft dynamics, it'll be hard to understand what's going on. But this is generalized, whether an aircraft, rotorcraft, or spacecraft student, these are some of the things you will understand. So let's look at this equation: mx double dot plus cx dot plus kx equals 0. Pretty straightforward. For initial conditions, because we have second order, we need two initial conditions. We need a position and we need a velocity. So let's go through the state space form again. State vector, state variables that are x and x dot. Nothing. It's pretty similar to what we did before. Instead of theta and theta dot, we have x and x dot. Now we do the same conversion, which is x dot and then x double dot. If we rearrange this equation, we'll get this. Pretty straightforward. Now we know x dot is from here, x2, and then this becomes x1 and x2. Now you can separate this and write it as, x dot equals ax in a matrix form, but we don't need that, so I'm not gonna go into it. And then let's see how that looks in MATLAB. So this is what we have from state space function. So now we have t and x, and then k, m, c. We once again define dx equals 0 to 2 by 1. And then we basically go dx of 1 is x of 2 again, and then dx of 2 is minus k over m x1 minus c over m x2. And that's it. Then what changes to the main script? Well, we did the same thing, and I'm just defining 0 to 10. I'm just changing the time step, so don't worry too much about it. And that initial conditions, now it's position and velocity. So I'm saying let's start at 1 meters and 0.5 meters per second. We define constants. C is equal to 0.5, K is equal to 1, M is equal to 5. These are all just random made up numbers that I use. But you want to make sure they're ideally the same units. So, mass is kilograms, this is Newton over meters, and this is Newtons over second, whatever the constant for damping is. You just want to make sure everything is consistent because it will affect the results. And then you call your solver. Copy there. So func t span init options k, m, c. 3 changes. And let's look at a case with no damper. So let's just set c equal to 0, which we can do. We can just say there's no damping. What do you think that happens? It looks very similar to what we saw with the simple pendulum. It just oscillates forever. But here, the blue is your position and the red is your velocity. And it's just oscillating. And I did it for actually 100 seconds in this case, just to show you that, you can do 1,000 seconds, it's going to keep doing that. But let's put in c equals to a finite value. What do you think that happens? Remember, c is damping. You are adding damping to the system, which means you're expected to have it die out. So for 100 seconds, you can see that the oscillation starts off, but it then quickly dies out, and you can play around with different values right here. And there you go. That's one way to simulate a system. Damping implies the oscillations will die down, and you can play around with different damping numbers and see what happens. You can change your, let's see, what you can change. So you can change these 3 parameters, because you can't change the initial conditions. They don't affect how the oscillations will happen. I used same initial conditions here, and I used same in the next case as well, right? It didn't change. It won't do anything. What will affect your entire problem is these 3 numbers right here. So you can play around with them. You can change your K and M and C to just make them go really fast, make it die down really slow. It's all up to you. And this is one great thing about doing this tool is that it kind of lets you analyze what's actually happening to the system. If I tell you damping 0.1 and 0.5, what do you think is different? Hard to say. If I tell you K is, if I say, for example, in this equation right here, K over M is 1, what does that mean? Or this K over M is 0.1 or K over M is 10. What does that mean for the equation? And how does it look like? And it's great to look at it visually with tools like this. Because I'm a space student and I want to talk about spacecraft, so I will do a shameless plug and talk about spacecraft here. So we'll look at the equation r double dot, r vector double dot plus mu over r vector is equal to 0. This is a second order equation, but it's a vector because r has an x, y, and z component here, and then this is just the norm. So you have 3 scalar second order equations. So if I write them in x, y, and z, this will become x double dot plus mu over r x, y double dot, and so on. So if you want to convert to state space vector form, each of these are second order. So that means each of them will have 2 first order equations. The total will get 6 first order equations. That means we need 6 initial conditions. It makes sense, we need position and velocity just like we did in mass spring damper, except our position is now x, y, z, and velocity is x dot, y dot, z dot. So the three scalar equations are x dot is minus mu r x cubed, y, and then r is x squared plus y squared plus z squared. And then we set our, now we have what we said, fixed state variables right here. This is the position and this is velocity. You have x1, x2, x3, x4, x5. So we just take the time derivative again. And then we get x dot, y dot, z dot, x double dot, y dot, double dot, z double dot. But we know what x dot, y dot, z dot, these three are just this. So we say x4, x5, x6, and then we, all of this is just these equations right here. So we plug that in, and then before we do this calculation, we have to specify that r is x1 squared plus x2 squared plus x3 squared square root, because I don't want to actually type that out. It just makes an ugly matrix vector. So you can just specify this earlier. We can do that. I am not going to show how it looks in state space form. I'm going to leave it as an exercise for you, but I will show you the results. So this is ISS, International Space Station. This is as of sometime yesterday, and I just simulated for like, yeah, pretty straightforward. Let's do that again. There you go. Now let's look at another orbit. It's called a Molniya orbit. It's used by the Russians for communications, so that this spacecraft spends a lot of time on top of Russia. So if you imagine this is like the North Pole and this is the South Pole, see what happens when I simulate it for like 2 days, 3 days, or something like that. You can see it starts off here, goes really fast, and then with just one orbit, you can see that it spends a lot of time in like the top half versus how much time it spends over here. Let's do that again. Slow, and it gets close to Earth, gets really fast, and comes back. And I just simulated for like one orbit. You can keep doing it again and again, and that's basically what it is. And that's something that's tells you by intuition. That's by design. It's made, the orbit's made like this. As you learned, ODE45 is quite a useful tool. There are plenty of dynamical systems for you to test it with. Now you can go ahead and take it along with your research. There's also a version of ODE45 in Python, in I think NumPy or SciPy, I'm not sure which one, but its use is the same, but its implementation might be slightly different, so you'll have to look it up in the documentation. But it's designed to work in a very similar way. And ODE45 is something that MATLAB has written and it's available, but you can go ahead and write your own algorithm if you are in a numerical methods class and like make it a more accurate method or however you want it to be. So it's all up to you how you want to use it. This is just tell you what you can do it with. You might not be looking to write an entire algorithm by yourself. Just let me use what MATLAB has. So thank you for attending this talk. If you have any questions, I will. I think I am allowed to unmute you. Let's see, attendees. Oops. Yeah, I don't see questions. 200 questions. Yes. So it will be posted under SAESAC page on the AE website, where we have all of our previous talks as well. If you go to the AE website, Student Live, you should be able to see it there. You can also email me afterwards at mnassif6@gotech.edu. You can also find me on the SSDL website and email me. I cannot guarantee I'll reply to you within 1 day, but I will be able to reply to you. Please don't email me asking, hey, can you take a look at my code? But if you just want to understand more or have more questions about how this method works, I'd be very happy to answer. If you want to request topics such as these, please feel, so these are some of the things that this topic came to me because I use it a lot. I was a TA for Spacecraft Flight Dynamics for 3 consecutive semesters with 3 different professors over the past couple of years, and I noticed that students did not know how to use ODE45 when I think this is something you should know in your sophomore, junior years. So I started this initiative at SAESAC, and we are looking at getting grad students to talk about, give lecture on topics like SDK, XFLR5, XFLR X rotor. So these are aircraft performance analysis tools, image processing, typesetting with LaTeX, etc. These are examples. It's not an exhaustive list. So if you want to request topics, you can look at the email that the AE department has sent out, and there's a Google form that you can go and request any topics, and we'll try our best to meet it. It all depends on whether we can get a grad student to talk to give a lecture on that topic, and are they available for that month? And we're hoping this is a test run. Ideally, we want it to be a interactive, face-to-face, in person, but obviously circumstances don't allow for that. So we'll keep them virtual. Lectures will be posted on the website. And I think they'll also be on SAESAC's YouTube channel. So, but we'll confirm about that. With that, if you have any questions, feel free to post on the chat. I will be around till another 15 minutes for you to ask any questions. So if you want to know where it will be posted, under Student Life, the AE website, you can find SAESAC, and the lecture recorder will be present right here. So SAESAC recorded presentations, and we'll post a link right here. How did I initially get involved with SSDL? I started off with when I first came to grad school, I was Dr. Gunter's advisor, and I joined the SSDL. So basically, I did my undergrad at University of Maryland, so I came here as a grad student, and I got assigned to Dr. Gunter because I was interested in spacecraft systems, and I've been with them since 2018. That's when I started. And now I'm conducting research with doing gravity science missions with small satellites for planetary exploration, and mainly at icy moons. Okay, I shall stop the broadcasting. Thank you for attending.